All right, so today we are in Algebra 2. Today's date is Thursday, January 9th, 2020. Make sure that your name and date are on your piece of paper. We are talking about interpreting exponential models. Thank you. Who can read our objective for the day? Quiet raised hand. I think Shui had it first.
Use rules of exponents to convert exponential equations to new forms to solve problems.
Yeah, and then I know there's probably a few people that are like, wait, rules of exponents? You're like, oh no, it's that same thing that we did last unit. And yes, it's the same thing that you did last unit. It does not go away. It never goes away. That's the kind of the fundamental rule of mathematics. If I taught you, it's just going to build on it. So, I think, are there only 3 examples? No, there's 5. Oh yeah, because there's 2 assignments. So you have 2 homework assignments tonight. Binder check tomorrow, test tomorrow. Here we go. So capital B is going to represent the number of bacteria. So notice that this equation is happening every 5 seconds. I know that because it's t divided by 5. I want to know how often or what's happening in terms of this common ratio every 1 second. Somehow I have to turn this 5 into a 1. How am I going to do that? Does anyone have an idea? Yeah, India?
You divide the scale factor by 5?
Not exactly divide by 5, but you're really, really close. You do something with that scale factor in 5. You want to take another shot, or should I help you out a little bit?
A little help.
Sorry, I missed that. Could you say it again, please?
Caroline.
If you could please have your backpack off of your table so I can make sure that you're...
It's over there.
No, it's not you.
It's Chewy. It's over
It's
there.
Chewy.
It's irrelevant. I'm over here. You would hear it.
But Leo, it still stands. If you could please put your backpack on the floor. Thank you. All right, so from here, know this rule. If I have x to the power of a over b, I can treat this as x to the power of 1 over b, and then I can still leave this to the power of a. Look at this. We have now gotten rid of the denominator by bringing it to the inside and leaving the outside. That's what we want. We want to leave this t on the outside and bring this 5 on the inside and then deal with that separately. Deal with them behind a dark corner or whatever. Okay, but we're going to deal with them and then turn this into a different number. And we are going to be using calculators. You can use the one that's on your computer for this. So unfortunately, for those of you sitting at your desk, I think just Oscar and Leo, that applies to you. If you're using your calculator, you have to just tilt your computer and then shut your laptop when you're done. So what we're going to do is we're going to say, hey, this 0.92 to the power of t over 5, that's really the same thing as 0.92 to the power of 1/5, all of that to the power of t. So the new question that I have for you guys is, what is 0.92 to the power of 1/5? And for that, you just need a calculator. That's not, I mean, you could probably do it by hand if you had the time, but let's use a calculator. So I highly recommend going to desmos.com/scientific using this type of calculator. I'll zoom in so people can see what the heck I'm typing. So again, I'm going to do 0.92 to the power of 1/5. So I'm going to do a fraction 1 over 5, not 65, 1 over 5, and I get 0.9834, and it goes on and on forever. I'm going to just round, let's do 0.9834. I'm just going to cut it off randomly, 0.9834. So this new equation is I'm kind of ignoring 1,200 because I don't care about the initial value. There's nothing in this question talking about the initial value. So this is now 0.9834. 9834 to the power, 9834 to the power of t. This rate is happening every second. It used to be every 5 seconds. Now it's happening every second because our denominator is 1. That's what we were looking for. Okay, so the first question that I have with a quiet raised hand is, am I adding or subtracting? Is this number bigger or less than 1? Yeah, Aurelio.
What happened to the Sindel?
The Sindel? Which?
I hung it up yesterday.
We were running low on whiteboards. Yeah, sorry, we had a ration.
That's a good excuse. I like it.
So, who has the music on? Is that me?
Yeah, it's
Weird.
my computer.
That is, I always assume it's Jaden now. That's so weird. Is this bigger or less than 1 for the base? Is it being added or subtracted to? Come on, you guys got this. India's already tried participating before. Beverly has her hand up. Other people? More people, more people, more people. Beverly's the only one with her card up. Go, Beverly.
What? I have to raise my card.
I'm not raising my hand again.
Say again? Yes, it is subtracted from because it is less than 1. Everyone can circle that. And then the next question is, well, since it's being added or subtracted from 1, now I have to do what is 0.9834 minus 1. You're always subtracting 1, right? And since we have calculators now, I can just come back over here to my calculator and say, okay, that answer, I can just hit -1 and hit enter. Oh, wait, I have to type in answer, I guess. By the way, if you type in ANS, that means answer. ANS, and it's exactly this answer that I had before. And I can say -1. And I know that I'm going down by this number. And if I say ANS times 100, I have now converted it into a percent. I'm going down by 1.65%. So I come back over here. Every second there is a 1.65% subtraction from the total number of bacteria. And there's my final answer. Once again, in case you couldn't follow the logic for what we did, I'm running through the entire problem again. We started with an equation that was every 5 seconds. We can check in the exponent. That's going to be a lot of these. You're always going to be dealing with properties of exponents. So look at the exponent. It's every 5 seconds. I want it every 1 second. So I needed some way to get t by itself, which I used the properties of exponents. I got t by itself, but now I need to figure out what is 0.92 to the power of 1/5. I use my calculator, and it is 0.9834. Now I need to say that it's subtracted from because it's less than 1. But how do I figure out that percent? That percent came from doing 0.9834 minus 1, this scratch work that I did off to the side. That would have given me 0.00165, or no, sorry, 0.0165. Move the decimal twice to the right, or multiply by 100, and you get 1.65. Question, Jaden.
So when I get like a decimal, do I just get like 4? Like you did 9834. Like do I have to always get like the last 4 or like?
I think if you do
First
2
4.
decimal places, it should be fine. I just did 4 to be super exact.
But I can just do 0.98.
I think 0.98 will still work, yeah. All right, so, and if you get stuff wrong with Khan Academy, maybe we'll amend that and say, oh no, it needs to be 3 decimal places, but I think 2 is fine. Let's try another one. Example number 2. All right, so we have a radioactive element that's decaying probably. Yeah, it looks like it's going to be decay. This is less than 1. And it's happening every t weeks. I need to see what's happening every week. This keyword here, every week. This is not every week. I can't even tell what's happening up here. 6t plus 3. Normally have t divided by something, t divided by something else. This is 6t plus 3. It's like super weird. How am I supposed to get just t by itself? Again, that's the whole goal of this question because we're doing every week. Every week means I just have a t over there and that's it. So how are we going to use properties of exponents in order to get just a t up here with other stuff, other kind of garbage numbers that we don't care about over here on the left-hand side? And I will show you, because if you haven't seen it before, it is a little bit difficult. But I think that we can all remember this property, that if I have a to the power, or let's do x to the power of a times x to the power of b, that was equal to x to the power of a plus b. Give your head a quick nod if you kind of remember that rule, roughly. Okay, got about 50% of you shaking your heads, yes. We're doing that rule backwards because I'm starting with something that's being added, and I need to go backwards to something. I'm trying to isolate that variable. So isolating that variable is going to give us this. I have 0.98, and I'm going to do this 6t first, so 0.98 to the power of 6t times 0.98 to the power of 3. These are the same thing. I'm using that property of exponents. I'm using this property, I'm going backwards. If I had a plus b, I'm separating it and keeping them multiplied with the same base. Okay, the whole goal is to get this t by itself. We're using the same rule that we just used in example number 1 now. I'm going to bring that 6 to the inside and leave the t on the outside. So I'm essentially just adding on a set of parentheses. I'm saying 0.98 to the power of 6 to the power of t. And now the t is by itself, just by isolating it with the parentheses. We didn't have to do anything fancy. And again, you kind of ignore this 0.98 to the power of 3 because that would be the number that should be in front. Like this 1,200. That's just a number. There's no variable in that. This is just a number, so we can ignore that. So I'm going to go ahead and cross this out. We don't care about the initial amount. We only care about the factor, the scale factor. I don't know what Leo's doing, but okay. So from here, I need to figure out what is 0.98 to the power of 6, and I'm going to simplify that. So this 0.98 to the power of 6, again, using your calculator, 0.98 to the power of 6, and I get 0.8858. So I'm going to say this is equal to 0.8858. 8858, and that is still to the power of t. I don't even need parentheses. That's to the power of t. And I ignore this initial amount. And that's the answer. Whenever I'm looking for a factor, the factor is whatever the base is. In this case, the factor is 0.8858. On Khan Academy, it'll tell you more specifically, round to the 4th decimal place or something like that. Round to the 1,000th or 3 decimal places. So this one is 0.8858. Yes, Anna.
What did we do with the 0.898 to the third?
You ignore it because that's an initial amount. Again, the initial amount is whatever number is out front. That's just a number with no exponent that has a variable. This doesn't have an exponent with a variable. It's just a number to a number. That is some constant term. This is the initial amount. I can even write that on here for the notes. This is the initial amount. And we don't care about the initial amount. We only care about the factor. And here's the factor right here. So we kind of ignored that. Yep, good question, good question. Other questions up to now? Otherwise, we're moving on to the next question. Question, Beverly?
Wait, so why did we turn it into a percentage in the first one and not the second?
When we turn it, this one was asking for a percent in the question, so we had to turn it into a percent that way. And why did we add or subtract from 1? Because it used the words add or subtract. If you ever see add or subtract, you're going to subtract 1. If you ever see the word factor, just leave it. Yep. Jane, can you please wait until after the lesson to do that? That's super distracting. All right, we're going on to example number 3, and then we have 4, 5, and 6, or 3, 4, and 5. All right, so we need to have this happening every t months. Oh, okay, this one is different. So instead of changing the exponent here, I need to change the base. Somehow this base needs to be turned into 3/4. So let's read the whole question. This capital M represents the mass of a radioactive element every t months. So it's not t over 4, it's not every 4 months, it's every t months. So there's our equation. The mass of the sample decays by a factor of 3/4 every how many months? So somehow we need to turn this into 3/4. Does anyone see anything interesting with the relationship between 27 and 3 and 64 and 4? And if you can't see that, look up there in the very top right because those numbers are up there, 27 and 64. What is special about 27 and 64? Who has their card still? India kind of half has her card. We'll give it to Anna.
They're both perfect squares.
Not squares, but
Or cubes.
cubes. Yes. So, can I give it India now? India, how do I rewrite that as cubes?
You, like, with the 3 or with the 27?
So 27 turns into what?
It turns into a 3 cube, and then 64 turns into a 4 cube.
It's 2 o'clock.
Thank you, Jaden. All right, and this is all to the power of t. So now we see a very clear connection, thank you, to 27 over 64 and 3/4 because I can now factor out these powers. This is the rule of exponent where you have this rule. If I have a over b, all of this to the power of, I don't know, let's do c, that is equal to a to the power of c over b to the power of c. It's kind of doing the reverse of that and we're about to apply that rule. If both of these are to the power, I can factor out that power and leave it outside the parentheses. So if I come back over here, this is now going to be equal to 150 times 3/4, which is what we wanted. We wanted the scale factor of 3/4, but I had to factor out this 3, and it becomes 3t. All right, and then there's a tiny little twist that I kind of alluded to in the first lesson on Tuesday, but now it's finally coming back. Normally, whenever we have a number in the exponent, we always say t divided by 3 means every 3 months. What happens if it's multiplied by t?
3 times a
With a quiet raised hand. Colby, yes?
month. It's 3 times a month.
It's 3 times a month, not exactly. How do we figure out, like, the answer's there. It's just looking us right in the face. Every how many months? It's not every 3 months, it's every...
That's what I meant.
I think it's, yeah,
That
I'll
is
give it to you
exactly what I
again.
meant.
Okay. So you have to take the reciprocal. You have to take it every 1/3 months. Because normally it's being divided by 3 and we say, oh yeah, every 3 months. Because it's being multiplied by 3, we say, oh, we'll take the reciprocal of that every 1/3 months. And there's our final answer. Now's the time to ask questions, otherwise we're moving to example number 4, which are very, very similar to what we're doing right here. All right. Example number 4. So, capital Y, when I do sub-minute, so capital Y represents the number of people in a crowd who yawn every t minutes. So here's our function. Every hour, the number of people who yawn increases by a factor of what? So the general question is, normally I do every minute. What happens if I turn this minute into an hour? What's going to happen with this ratio, this factor here? So the general question before we move on, the conceptual question is, should there be more people yawning every hour or less people yawning every hour compared to the minute? So do a thumbs up if you think there's going to be more people yawning every hour. Thumbs down if you think there's going to be less people yawning every hour. All right, looks like all of you have the conceptual understanding. More people, because an hour is bigger than a minute. So there's 60 minutes an hour, so it should be almost 60 times bigger, right? Well, not 60 times, it's exponential. But it should be bigger because this is a bigger interval. And I need to make that explicit because that gets confusing really fast. So we say hour, which we want to have something in an hour, is bigger than a minute. Therefore, our factor, so because of this, let me say, therefore, we can say this implies that our factor should now be bigger than 1.02. That's my notes for the logic. Because we're making the time bigger, this number should be bigger. From minute to an hour, I'm trying to get bigger. This should therefore be bigger. 1.02 is bigger. Yes, Anna.
So if you increase the time, the amount of whatever you're measuring also increases.
Yes. So the question would be like, am I going to do to the power of 1 over 60 or am I going to do to the power of 60? And the answer is to the power of 60 because I'm trying to make it bigger. If I want to make it smaller, I do to the power of 1 divided by 60. But this one, I want to make it bigger, so I need to convert this. And on my scratch work off here to the side, I need to do 1.02. Can someone give me a quiet raised hand just to make sure we all understand this? How many minutes are in an hour? Quiet raised hand, easy to get your card in.
Sorry.
Jaden?
60.
60, yeah. So this is going to be 1.02 to the power of 60. We have our calculators. So come back over here. 1.02 to the power of 60 is 3.281. I'm just going to round to 2 decimal places now. I know I'm kind of all over the place. 3.28. So that is equal to, it's approximately equal to 3.28. And that's the fact that it's looking for. Whenever you see the word factor, just write whatever the base is. This is the base, 3.28 now to the power of t, so it's going to be 3.28. Again, you only have two options with these types of problems. When you're converting between times, you're either going to multiply by, or you're going to take it to the power of 60, or you're going to take it to the power of 1 over 60. It's either going to get bigger or smaller with the exponent. Let's go on to our final example. Example number 5. Question, Beverly.
What if it doesn't say factor?
If it doesn't say factor, if it says a percent or something, then you need to subtract 1. And then turn it into a percent. Yep. Good question. All right, so I don't know if it ever happens on the homework. I haven't checked, though. So now we're going to have something that has something with a year. Capital B for a year represents total number of branches on a tree. And it's going to keep growing more branches throughout the year. Jaden?
Sorry, I was just getting the calculator. I
Okay,
I'll show
I'll
you.
believe you because we have trust. So I have this equation for branches on a tree, but every month the number of branches increases by what scale factor? So again, the question is, I had something from a year and I'm going to a month. Am I getting bigger or am I getting smaller? Smaller, thumbs down, or bigger, thumbs up? And everyone is looking like they have the correct logic. From a year to a month, am I getting bigger or smaller going from a year to a month? I'm getting smaller because a month is smaller than a year. That means I should be getting smaller. So I'll just say something along the lines of month, which we want to get our form into a month, is smaller than a year. That implies that our factor should be less than the original factor, which was 3.2, so our factor should be less than that 3.2. So what are we really doing in terms of our math, our scratch work? Well, I had 3.2, and I'm now going to do it to the factor of 1 over something. 1 over. Well, again, what number should go here? 1 over what? Quiet raised hand. India? 12. Why 12? You're correct.
Because there's 12 months in the year.
12 months in a year. Exactly. So I come over here, I do 3.2 to the power of 1/12. And it's 1.102, I guess. So this is approximately 1.102. And it's increasing by a factor. Whenever I see the word factor, I just write whatever the base is, which is, in this case, 1.102. 1.102, final answer. That's all I have for you guys for the notes. Are there any questions on the entire set of notes? No. Okay, let's do FISA 5 on our objective. How well can you use rules of exponents to convert exponential equations to new forms in order to solve problems? 4, 3, 3, 3, 3, 2, 3, 5, 2, 3, 3, yawn, 3, and 3. All right. So those numbers will eventually get higher and higher.
Can you go back down?